All right. Hi, everyone. Thank you all for joining us. So we are going to get started with our webinar. So as you just heard, this webinar is being recorded. It will be available on our PSC YouTube channel, which will also be linked on our Neocortex webpage, which is, you may have seen our webinar promoted on there online. So we will send that out in a follow-up email following this webinar. So in our webinar today, we're going to have about 45 minutes of presentations. We'll have two presentations, and we'll start off with Paula, who is the PI of Neocortex, and she's PSC's AI and Big Data Director. She'll give us an overview of the project, and she'll share more about the upcoming call for proposals. So we will hope that you guys will participate in our webinar. So what you can do is you can ask questions via the Q&A feature in the webinar. So what you can do is there's a Q&A button that you have available to you, and you can type questions in there, and then our panelists can see those. They will either respond verbally or they'll type their answers out to you. And if we need any clarification or we need to chat with you, you can also use the raise hand function if we need that. And we'll be doing most of the Q&A at the end of the webinar. We'll save about 15, 20 minutes for that. So this webinar abides by the XSEED Code of Conducts, which Paula will pull up now. So we just wanted to make everyone aware of that. So we promoted this via XSEED, which you may have heard about, and you may have found out about this webinar from XSEED. So they have an external code of conduct, which follows our commitment to providing an inclusive and harassment-free environment. And that's just something that we follow as a partner of XSEED, and we wanted to make sure that everyone was aware that we are following this code of conduct and that everyone is abiding by that. So with that, I will hand it over to Paula to kick us off.
Thank you, Megan. Can you hear me well?
Yes.
Good. Thank you so much. So let's go ahead and get started with the first part of the webinar. We are going to have an overview of the project and also share some details on the upcoming call for proposals, where we expect to attract the next round of users for our system. So this is an overview of this first section. We are going to talk a little bit about the context of the project, what motivated the project, then we'll have a short hardware description. And we'll also cover a brief summary of our very successful early user program, which we concluded in summer of 2021, very recently, and talk a little bit about a couple of exemplary use cases. And then I'll go and describe how is the upcoming call for proposal going to be. These are Neocortex systems. These are pictures taken from the system that is currently deployed in our PSC machine room, which is located in Monroeville, very close to Pittsburgh in Pennsylvania. What we can see on the left is one of the Cerebras systems. We have two of them. They are stacked one on top of the other. And then to the right of the Cerebras systems, we have our Superdome Flex, which uses a whole rack. The system is deployed or was delivered by Cerebras and Hewlett-Packard Enterprise. And it is funded by NSF, and as I will describe in just one moment. So Neocortex was proposed in response to NSF Solicitation 19587, where NSF was requesting proposals from organizations to serve as service providers. This was to enhance the advanced cyber infrastructure capabilities in response with the aim to support the full range of research that is based on computational and data-intensive capabilities. This, of course, across all science and engineering in the United States. Now, the one thing that is worth highlighting is that they were requesting two types of systems or two categories. Neocortex was proposed in response to category 2, which is described as innovative prototypes and testbeds. The goal of these category 2 systems is to try out forward-looking capabilities, where novel technologies, architectures, or usage models are explored and aim to target or satisfy the needs of specific parts of the community or research that is advanced by the community. So Neocortex is a system that is expected to last 5 years. As I mentioned, was delivered by Cerebras and Hewlett-Packard Enterprise. And it is comprised or is funded by $5 million for acquisition and then $5 million for operations. So up to this is outdated. So more money has been awarded up to now, a portion of the operations part and also all the acquisition section or phase or part of Neocortex. Now, what are some of the goals or the kind of overarching goals of Neocortex? On one end, our first goal was to deploy the system, Neocortex, and with this, offer the national open science community access to revolutionary hardware technology. All of this with the goal of accelerating AI training at unprecedented levels. Once we deploy Neocortex, our goal is to continue exploring, supporting, and operating Neocortex for at least 5 years. And then one of the main goals of this project, given that it features this interesting and promising hardware technology, is to work towards engaging a wider audience and then foster adoption of these innovative technologies. Just a quick comment, we are currently working towards setting up additional kind of channels where we provide user support and where we disseminate experiences and best practices. As some of you might be aware, recently on PERC 2021, we had a very interesting panel that I invite you all to go review the recording of this panel, where we have users share their experiences and address questions from the audience. Now, I'm happy to share that we have crossed this out of our to-do list. We have successfully deployed Neocortex, as the pictures I initially showed demonstrate. And we have also successfully run an early user program, which I will be talking more about in the next slides. A little bit about the timeline of the project. The project was awarded in June of 2020. Since that day, we started working toward preparing for the system. We have a number of webinars, working towards setting up the system and user environment, deploy some documentation, content dissemination, and started preparing for the early user program. In fall 2020, we started delivery, installation, and initial testing of the system. February 2021, the system was fully deployed and integrated, and our early users gained access. And in summer of this year, we concluded the early user program and the acceptance testing. And more specifically, in August of this year, about a month and a half ago, we officially started what we refer to as the Neocortex testbed operations. So prior to August 2021, we were in what we describe as the acquisition phase. We successfully completed that phase and then transitioned to testbed operations. And now here we are in October 21, where we are announcing the call for proposals. So our next round of users can join the project and come leverage the great technologies that we have in Neocortex. Now let's talk a little bit about the motivation behind Neocortex. As we all might be aware, AI is a field that is rapidly evolving, and it's all the time hungry for more and more compute. This is a graph that many of you might have seen from the Artificial Intelligence Index report by the Human-Centered Artificial Intelligence group in Stanford University. It features what would be the compute needed by state-of-the-art models over time. And we see two eras, one that was prior to 2012, and the second one starts on 2012 and onward. What we see is that the state-of-the-art AI models prior to 2012, the compute they were requiring was doubling every 2 years. But past 2012, when AlexNet and all that revolution, the compute needed has been doubling every 3.4 months, roughly. These are two graphs that show computer vision models on the left and natural language processing models on the right. The trend that we see is that models are becoming larger and more ambitious. The more complex the problems they are trying to address, the more complex the models become in terms of parameters, and also, as we know, the larger the data sets are that they process or that are required to train them. Additional sources of complexity come from specific types of approaches like generative adversarial networks, domain adaptation, reinforcement learning, where we have external cycles of training, and in each of these cycles, the training of a particular model is needed. So not only we need to train these very large models with very large data sets, but then a specific paradigms approach or require the training of these models a large number of times. So with this in mind, what we are aiming to do here with Neocortex is to create revolutions similar to the ones that have taken place in computer vision and natural language processing, but in scientific domains. We have already seen that happening. As an example, we have here some of the computational predictions of the folding of proteins that was done by the different versions of AlphaFold. So what we are aiming here is that Neocortex enables it kind of breakthroughs in different science and engineering domains. So with Neocortex, we expect to transform and accelerate AI-enabled research, expect to support the development of new and more efficient algorithms and models, and also algorithms for graph analytics. We also want to continue supporting the integration of artificial deep learning with scientific workflows in the form of surrogate models and alike. We also recognize the need, as mentioned before, that in order to make these breakthroughs, it's important to have access to game-changing compute power. That's one thing that Neocortex certainly addresses. And in the spirit of being a Category 2 system, we are also exploring the potential of very promising and groundbreaking new hardware architecture. One of the elements of Neocortex also features very large scale memory features and that are great for genomics, brain imaging, simulation modeling. So that type of research is within the scope of what Neocortex supports and continues or aims to continue supporting. And all of this while working towards making sure these capabilities are very usable, are documentation and all of the resources needed for users to make good use of the system are available. So let's talk about the hardware specifically that is featured in Neocortex. Neocortex, we have two Cerebras CS-1s. This is a summary of kind of the specs. It's also available on the Neocortex webpage. Each of the CS1s features a Wafer scale engine. We will have more information, technical details in this in the second section of this webinar. But each of these Wafer scale engines has, well, as you might have heard at the time, it was the largest chip ever built. It has 400,000 sparse linear algebra compute cores, 1.2 trillion transistors. So it's a very powerful and interesting chip to use for AI. It also has 1.2 terabytes per second of system I/O. These two Cerebras CS1 servers are also interconnected or tightly coupled with a HPE Superdome Flex server, which in itself is a wonderful compute machine, and which has 24 terabytes of RAM, aggregate memory bandwidth of 4.5 terabytes per second, very large local disks, and it's also interconnected with bridges to leverage the great capabilities that we also have in that system. So more graphical representation of Neocortex looks like this. We have the two Cerebras CS1 servers interconnected and at 1.2 terabits per second to the HPE Superdome Flex. And then the Superdome Flex is also tightly coupled at 1.6 terabytes per second to bridges 2. In bridges 2, we have very powerful ocean file system and jet file system. These and that provide capabilities for storage, and also we have very great compute capabilities for traditional or a little bit more traditional compute needs on bridges too. So what we aim to do here is we want users that would mainly use Neocortex, or maybe users that have a very large demanding simulation workflow that run some bridges too, and maybe one of the steps of the workflow is very ambitious in terms of the compute needed for their AI side and leverages what is on Neocortex. A couple of graphical representations of what we have on the Cerebras CS-1. As I mentioned, Natalia, in the second section of the webinar, will just dive a little bit more deeper on the technical side of the servers. But this is how a Cerebras CS-1 server looks like from the inside, and this is how a Wafer scale engine processor looks like. There is a baseball. For comparison, chips normally are way smaller, but this one is a very large wafer. Some of the specs of the Cerebras CS-1, as mentioned, is the largest chip ever built at the time. Very powerful on-chip memory, which makes all the data to be one clock cycle from the cores. So that certainly accelerates and helps speed up the training task. We also have 9.6 terabytes per second of aggregate memory bandwidth. This is not a single memory that features this speed, but it's the aggregate throughout the chip, just for clarification. One thing to mention here is that in order to use this very powerful server and chip, what is currently being supported is TensorFlow and PyTorch. So users that have their code in TensorFlow and PyTorch can, in principle, very seamlessly transition to leverage these powers of full system. I won't dive any more. Well, I won't, like in the interest of time, I will allow Natalia to share more details on the technical side of the CS-1. Now, the Superdome Flex, as mentioned, is a very powerful, very large memory system on its own. What it's designed to do, or was designed to do, is to provide very substantial capability for everything that is pre-processing and post-processing, all the complementary aspects of AI workflows. As many of you might be aware, those of you that have done AI or training, one thing is to train the model, but all the tasks that take place prior to having your data ready to train your model, and all the post-processing pruning of models that need to take place after the training are on their own very demanding. The Superdome Flex is also designed to support very large data sets and to feed the CS-1s at a very fast speed. And also, it is designed to also support both CS-1s independently and at once. So one of the goals of the project is at one point in the future to explore the scaling of the CS servers. That would be to be able to use more than one CS server for one training task. That's the task still to be explored. With that, I conclude the description of the system, like the hardware capabilities. More details, as mentioned, are available on the web side of the project. Now I would like to talk about a little bit about the early user program that we ran. We received 42 project proposals for the early user program. We have applicants from 21 institutions. We encourage all attendees from any of these institutions or from other institutions to apply for our upcoming call for proposals. And just to share some numbers, we had in our early user program 17 projects with whom we work very closely. A little bit of the dissemination activities for your reference. If any of you is interested in going on and reviewing any of them, we run 5 webinars and training spaces, and also have 14 speaking engagements in conference, university classes, and academic workshops. There are 2 scientific papers published. All the information is available in the slides, which will be made available through the project website once the webinar concludes. And we also have a project, well, as mentioned, the project website, but also have social media channels where we constantly update on upcoming opportunities. So let's talk about a couple of projects that were, for example, in an early user program. This is from the University of Michigan. And what this project aims to do is support the diagnosis of acute respiratory problems, which I understand 65% of patients diagnosed or that have this condition are diagnosed late or are misdiagnosed. Every day that passes without having a correct diagnosis increases the mortality rate, which at the time is 35%. So this is a project, a group in University of Michigan that leveraged the unit architecture to properly diagnose or segment lung images, enable to in a fast way diagnose this condition. So what they have been leveraging Neocortex for is to do a very ambitious and complex hyperparameter tuning of their network in order to maximize the accuracy of the results provided by the network. More details on this are also available through the panel that we have. We had this user participate in the panel from that we had in part 21, where they explain in more detail all the context and what they have been able to achieve thanks to Neocortex. The second example case that I have is from CMU by our colleagues Kit Puthi, Matthew Gothenberg, Venkatesh Vanathan. Apologies if I'm mispronouncing this, most likely. What they aim to do here is model isomers and their molecular energies. They had a model that had limitations in terms of the quantity of data that they could process. They have been able to process a way larger data set, a couple scales of magnitude larger than what they were able to do prior to joining Neocortex, and also have been able to specialize their code and make their model a little bit larger while keeping the training times within a reasonable time frame. We will be publishing on Neocortex, the website, more details on the use cases or success use cases that we have had throughout the project, throughout the early user program, and we expect to have way more with that call for proposal. Now, let's talk a little bit about the call for proposals. We are expecting to make it available this week, and all details will be at your disposal in the Neocortex webpage. It's open to almost all US-based university and not-profit researchers. We will use, once again, EasyChair as the way to receive applications and process them. We expect the CFP to be open for about a month. And one thing that will happen during in the CFP is that applications will be evaluated as they come in. So as soon as you apply in that week, we'll have our team review it and potentially contact you for more details or provide a determination. Again, similar as when we have our CFP per the EUP, we'll have a very lightweight application that will be a 5 to 6 question form. And based on that information, the information you provide, if the information is complete, we would make a decision based on that information. But if necessary, we will have follow-up meetings as possible to confirm the scope of the project and where the project is currently suitable for the system or not. Our expectation is that we'll have the next round of users onboarded by late November, early December. What projects or those users or projects that are selected, what they get is an allocation Neocortex and a small allocation on certain bridges to resources that is complementary for the work on Neocortex. By default, we grant this by a year, but if you need a different period of time, that is also something that you can mention in your application. What you can expect to happen is that as soon as you're selected, there will be a very close collaboration and very constant communication between you and your team, PSC and vendors, vendors being here, Cerebras and HPE. Throughout your project, something that we encourage and welcome and expect is feedback and you sharing your user experience so we can further strengthen the project, all that is documentations and the resources that make available to those that are using Neocortex is very useful as we aim to improve and make sure the system is easy to use. Now, we'll have more technical details on the Cerebras servers, the framework supporters, and the current application in terms of which ones are ideally suited at this time in the second part that we'll have in one moment by Dr. Vasileva. With this, I know we have a very short time, so I'm happy to address questions in the Q&A. I would like to once again extend my gratitude to everyone contributing to Neocortex, Cerebras, and Hewlett-Packard Enterprise for delivering the system, NSF for sponsoring it, and certainly all our Neocortex team at PSC who has made this project available, and we continue to support and work closely to enable all the science, great science and research that our users do. Here in the slides, you'll have the links to the Neocortex website, also how to join the Neocortex updates list, information on how to apply for the upcoming CFP, which, as I mentioned, we expect to make available throughout this week. And also through the website, the project website will be the way to know more about our upcoming or the Cerebras technology user group that we are working towards. And our official email where you can send questions, requests, comments, suggestions is neocortex@psc.edu. So we encourage each and all you to participate via these channels. With this, I would like to pass it on to Natalia. For the second part.
Thank you, Paula, and hello, everyone. Hope you can see my screen. So let me take over from here. I will tell a little bit about CS1 system, motivations for building the system, what's inside, what it looks like to program the system. Hope to do that in roughly 20 minutes, so we have some time for the questions. So CS1 systems are essentially accelerator inside the Neocortex. So we have two of those systems as part of the Neocortex, as Paula mentioned, and they serve as accelerators for mostly deep learning workloads. So first, starting with an observation, we are facing today significant growth of complexity and size of those deep learning models. The driver domain is probably natural language processing, where the size of the models now is beyond imaginable. So people train models with hundreds of billions of parameters and aspire to train multi-trillion parameter models. It all requires a lot of compute. But in computer vision and other domains, the requirement to compute is also very, very significant. And if you look at existing compute resources used to train those models, if you train them on a kind of single device or a small scale systems, it will take enormous amount of time to train. So for those large scale NLP models, which I show on the slides, an estimated time to train on something like a single DGX server ranges to very long training time. So what people do today to tackle that, they try to kind of cluster multiple systems together and train those extreme models in a distributed fashion. But the distribution provides diminishing returns. So on the slide, I also show some data from their latest training results from MLPerf training for BERT model, which is by far not the largest ones out there, but probably the most commonly used in natural language processing. So as you can see, as we go from kind of single to 512 DGX servers and increasing the number of GPUs, the speed ups is nowhere near linear. So when we go from 1 to 512, we get a speed up of 67 times. So at this scale, every kind of additional device you add to tackle that problem does very little. And there is only so much you can do when you have to deal with this interconnect and memory bottlenecks across the dozens of hundreds of devices. Also, one additional factor that comes into play is the default parallelization mode for these workloads. So most of the models today train with data parallel training, meaning that you increase their size of the batch, which you use to make an update. And that kind of hurts typically convergence of the problem. So the diminishing returns, which you see on the slide, comes from kind of two factors. One, as you scale to larger clusters, the communication becomes a bottleneck. And second is due to scaling using data parallel, you see kind of diminishing returns of convergence, and you need to increase a number of epochs to train the model to the target size. So essentially, from this, we can make an observation that in order to train those models efficiently, we ideally want more compute on a single device, so we don't need to go to distributed training as long as we can. And also, we want to rely less on data parallel training and hence be less dependent on those large batch sizes to utilize the hardware. And at Cerebras, we attempted to do exactly that. So we built a Wafer scale engine, which is the most powerful processor for training deep neural networks. That's the largest chip ever built in production. By today, we have 2 generations of the chip released. Today in production, most of the systems run Wafer scale engine 1, and that's the chip which is installed in the Neocortex. And we are just starting to sell systems with Wafer scale engine. So the first deliveries will be later this year. So in each of those chips, we have hundreds of thousands of cores, and each one of those cores is designed for sparse linear algebra to accelerate training and inference of deep neural networks. So we tackle the problem of scale. So we pack very large number of cores on a single device. So we try to enable training with of larger models without the need to go to distributed programming. And we also optimized every single core to be efficient at the types of operations which are required when you run training and inference of deep neural nets. So we have a lot of cores, we have a lot of on-chip memory, which enables us to run at high utilization with low batch sizes. We can do operations with very low arithmetic intensity really well. And all of those hundreds of thousand cores, because they all sit on a single piece of silicon, they have enormous interconnect. So that means that we have flexibility to choose any distribution strategy. And as a matter of fact, we typically choose some flexible blend of model parallel and data parallel training depending on the model. So as a result, what you have, essentially, you have a cluster scale compute, but on a single chip. So you don't need to rely on distributed training. You can still operate as a single device, but get the performance of a typical cluster of several devices. We package that chip into a special build system. So our CS1 and CS2 systems entirely build around the needs of Wafer scale engine. So it's been custom built to power, cool down, and deliver data to the chip. It's only 1/3 of the size of the standard data center rack. You've seen in the pictures that Paul showed that we have 2 of those systems packed into a single rack for the Neocortex system. So it's been built to make it easy to install and to get going with and kind of to connect to the rest of the infrastructure. The third very important component of our solution is our software platform. So we have chip, we have system to cool down, power, bring data to the chip, but how do you program the chip? You program the chip with the help of our compiler for deep learning workloads that allows us to program transparently in TensorFlow and PyTorch. So we have interface level integration. We extract the computational graph directly from TensorFlow or PyTorch code, and then our compiler takes care of mapping the computations inside your definition of your compute graph into our library of high-performance deep learning kernels. And then also our compiler automatically assigns an optimal amount of cores for every core, for every kernel, so that overall performance of the model is as optimized as possible. There is also an opportunity to extend that library of handwritten kernels using Cerebras SDK, which will be released really soon. And once you gone through the compilation step, essentially at the end, you have an executable which is generated automatically for you and which will be loaded by our software onto the system. And you can run training on CS1 or CS2 systems. So again, you get a cluster scale performance, but with the ease of programming of a single node. So summarizing what we are building and what every package of our solution has is the centerpiece, wafer scale engine, so wafer scale compute system to cool down power and bring data to the chip, and our software platform, which enables to program that chip. So now let's dive in a little bit into two major components, wafer scale engine and our software, and how you program essentially the chip. So the wafer scale engine is a 2D mesh of hundreds of thousands fully programmable processing elements. Every single processing element can be programmed independently and has local memory, compute, and a fabric switch or router to route the data. So looking a little bit more into what's inside that processing element, each component, that processing element has been optimized and designed to run very efficiently linear operations on sparse tensors. And since those operations are roughly 90% or more of operations when you run training or inference of deep neural nets, that's a really good fit for deep learning. So let's look a little bit into the components of the chip. First, the central component of any core is compute. Our compute is fine-grained, it's fully independent and fully programmable. So every single core can be programmed independently. It has hardware data flow mechanisms to enable dynamic execution, and it also enables acceleration from sparsity. It makes it ideal kind of for changing neural network and increasing to come up with the new models which can leverage sparsity and which can reduce algorithmic complexity of training those models. We can translate that directly to the speed up. So the second key component of processing element or any device is memory. So every single processing element has local memory on chip, has SRAM. So the memory is all kind of fully distributed, the whole memory of the overall wafer scale engine. It's just a combination of local memories of each of the processing elements. So every processing element operates on the data inside. And the third key component is communication. So every single processing element connected to its neighbors up, down, right, left, and has very high bandwidth, low latency interconnect with the neighbors. The fabric on the chip is also fully configurable for a specific workload. The configuration is done at compute time to maximize the bandwidth for a particular workload at hand. So what wafer scale means for deep learning and what are the advantages of wafer scale for deep learning? Again, we have a lot of compute, we have a lot of optimized cores. So that means that we have that cluster equivalent compute on a single node, on a single chip. We have high speed on-chip memory. That means that there are no memory bottlenecks and we can operate at low batch sizes, and we can also efficiently support operations on sparse tensors, which has low arithmetic intensity compared to dense matrix-matrix multiplications. And they have more fabric bandwidth at low latency, which enables us to kind of flexibly explore all parallelism in the workloads and choose what's best for a particular workload for a particular application. So altogether, again, it gives us cluster scale acceleration, but on a single chip. Diving a little bit deeper into advantages, I think key components of the advantages of wafer scale engine for both deep learning and HPC, and why we talk about this sparse linear algebra. So I think the key recipe, in addition to scale, is really this memory bandwidth, which allows us to run +1 operations, so vector-vector operations at full utilization. So in a typical processing elements like GPUs or CPUs, you always have memory hierarchies. And those memory hierarchies kind of break an ability to run with high utilization on vector-vector operations. So you can only get to high utilization on matrix-matrix operations. what we do on our chip, because we have that enormous memory bandwidth, we essentially implement matrix vector, vector, matrix operations, all implemented as cycles around vector operations. And that gives us an ability to, again, harvest sparsity. We can treat sparse matrix multiplication as just a scalar vector operation. We can operate that at full utilization. So that's one of the key advantages of the chip. And we leverage that for both deep learning and also have some early examples of HPC workloads, which can benefit from that as well. So that was a little like how we review of the chip. Now let's take a look at how the chip is programmed and what's inside the software. So today we can program CS1 in 3 different ways depending on the application. For deep learning, we have integration, very tight integration with standard deep learning frameworks. So we have capability to interact and allow high-level programming with the standard ML frameworks like TensorFlow and PyTorch. And also there is an ability to create custom kernels with our SDK. We also have examples when people run hybrid AI and HPC workloads, when HPC codes run simulation on outside of our accelerator, but then part of the simulation job is approximated by a neural network, and HPC code sends inference request to run that approximation during the simulation job through C++ interface. So it enables kind of direct integration with the HPC codes, and it allows those hybrid AI and HPC workloads. And the third, very early stages, we also have an ability to run kind of HPC code on a system by programming the device directly through Cerebras kernel SDK. So we have C-level programming interface, which will be released in a matter of weeks. We will have a beta release of Cerebras kernel SDK, which will enable to program some HPC workloads. So talking a little bit more about deep learning first. For deep learning, we have 2 execution modes. The first, which has been supported historically, and our production execution mode for today, what we call pipelined execution. The key features of that execution is that we essentially load the whole model onto the chip. We keep the weights stationary in memory in SRAM of the chip, and we stream data and we stream activations through the chip. So this gives us an intrinsic ability to leverage activations and delta sparsity. It also gives very low latency, and it's a very efficient way to run training of the models which can fit on the chip. So if the model can fit into 18 gigabytes of memory of CS1 or 40 gigabytes of memory of CS2, pipelined execution typically is a really good way to train the model. And then we have also secondary execution mode, which we call weight streaming, which swaps the role of weights and activations in the sense that now we kind of load 1 mini batch of data onto wafer scale engine at a time. We keep all the model into external model memory, and we stream 1 layer at a time weights to the model to run training. This enables us to train models of a size which doesn't fit into memory of the chip, and that execution mode is kind of more similar to how GPU and other accelerators operates. How we choose which execution mode to choose depends on the model size. So for typical sized models, roughly below billion parameter, we choose pipelined execution mode. For models of extreme size, we choose weight streaming execution mode. What it looks like to kind of write the code for CS1, I have a couple of examples, one of them for TensorFlow. So here you see that we heavily leverage estimator API. So we have our own wrapper around standard TensorFlow estimator. And this kind of snippet of the code, I highlight with color the lines of code which are Cerebras specific. So here we, instead of leveraging standard TensorFlow estimator and standard TensorFlow configuration object, we use Cerebras wrappers around, and then kind of the rest of the code can stay the same. So the rest of the estimator API stays whole. We also have early examples with the PyTorch. Beta support for PyTorch is coming up also within a matter of weeks. We have that PyTorch integration running in our lab today. So integration with PyTorch is also done on a kind of high-level interface level. We use PyTorch XLA backend to extract the computational graph from the PyTorch, and when we are tracing, we use tracing to extract the complete PyTorch graph from your code. In terms of the writing the code, the changes which you will have to make, you will have to import our Cerebras PyTorch based model. And then when you choose which device to use to run, instead of choosing GPU or CPU device, you use XLA device. And that's pretty much all the changes to the PyTorch code. So that's about how you program with the ML frameworks. I mentioned also that we are releasing Cerebras SDK. That's a complete new package to enable low-level programming for either custom kernels for deep learning or for completely custom applications. So most of the HPC applications will be written using Cerebras SDK. So that's a general purpose platform and API for software developers to program for our chip at a low level. So it consists of language and some libraries and tools for debugging. In terms of language, when you program CS1, you will have to program some operations running on a host, which is CPU hosts. So there you will use Python APIs, but the main goal is to enable you to program for CS1, CS2 for Wafer scale engine. So for that, we have our own domain-specific language based on C. So for those of you who wrote kernels for CUDA, that will look really familiar, and that language also uses very familiar parallel programming concepts. As a part of the release of the SDK, we will also release a few reference implementations of most commonly used primitives and most commonly used operations, so things like BLAS, FFT, and others, which can be used first as an example to see how the code is written, but also you can just use that to plug into your code. So the release of the SDK is planned, the beta release is planned for mid-October, so in a couple of weeks. So by the time when the new wave of users arrives onto the Neocortex system, we expect SDK to be available. And just as a summary, last few points on how Neocortex operates and how it looks like to run things on the system together with the Superdome Flex and what comes where. So CS1 device is a network attached accelerator. So as Paula showed, we have two CS1 systems attached through the switches to the Superdome Flex. And from the user experience, user always interacts with the Superdome Flex. So you SSH into that standard system running Unix, and you have your code staged either locally or in network file storage. And essentially you just run inside Cerebras environment compilation process, and you start any jobs within the very familiar environment. So our software deployed on Superdome Flex in Singularity container takes care of compilation and takes care of managing the connections to CS1 and routing the data to CS1 and the results of training jobs out of CS1 back to Superdome Flex. So essentially you interact with the Superdome Flex and run within our environment to run the jobs on the CS1 systems. And probably the last thing I would like to to mention is suggested focus areas for upcoming call for proposals. We encourage the proposals in the following areas because we believe that's a really good fit for the system, and it enables to utilize fully CS1 systems. We've seen a lot of success training domain-specific natural language NLP models. We are self-supervised pre-training with transformers, attention-based models. Also, there were several interesting experiments also on language modeling side with the wide and shallow LSTM models, and we know that our system is a really good fit for those because recurrent models are hard typically to run on GPUs. And any other application of attention-based models. So things like machine translation with sequence-to-sequence modeling with transformers, things like applying attention-based models for building protein embeddings, embeddings for DNA. That's been also really advantageous in the system because usually for, let's say, for DNA data, the data sets are really large, and we can accelerate those tremendously on a system. So on a slide, you can see a few examples of training, and also we encourage, and we've seen some interesting examples where our system has been used for inference, especially for inference on very small models where it's hard to get high utilization on GPUs. And we've seen quite significant advantage of that on our system as well. So with that, if you want to read more about Cerebras system, I encourage you to visit our website. We have a collection of white papers, blog posts, customer stories, which explore what has been done on the system already and give you a better feeling on how the system works. With that, I will pass to Megan to manage our Q&A session.
Okay, thank you, Natalia. So we have a bunch of questions, and I know that Paula answered a few of them. So everyone should be able to see any questions that have been answered, so you can see the answers to those. But as far as the open questions, I will field those to our panelists. So firstly, and this question came in during Paula's presentation, but I think, Natalia, you might be able to answer this. Maria asks, what does it mean for the cores? Are AI optimized in terms of the architecture of the cores?
Yeah, so that means that essentially the architecture of the cores has been designed to make sure that we can do those linear operations on sparse tensors really fast. And also the fact that the chip has a data flow architecture enables us to kind of efficiently map their neural network onto the chip and kind of trigger the compute when the data arrives. So we see high utilization of our cores for those types of operations.
Okay. So then the next question says, can LAIR, L-A-I-R, be used to write programs that are not TensorFlow or PyTorch based?
So for the programs which are not TensorFlow and PyTorch based, means that you will need to leverage our kernel SDK to program the wafer scale engine device directly.
Okay. So then someone asks, when I adopt my TF-based application for running on PSC with Cerebras, what changes do I need to make?
Yeah, that depends on how your TF code looks like today. If you today leverage Estimator API for your TensorFlow implementation, then the changes will be minor. So you will have to replace TensorFlow Estimator object with the Cerebras wrapper, Cerebras Estimator, and also TensorFlow configuration object with the Cerebras configuration object. If you previously have your TensorFlow code, which deals directly with the compute graph sessions, then you will have to adapt that code to essentially follow the estimator guidelines.
Okay, so next up, while programming deep learning models, should we treat this as one big machine akin to a GPU with 18 gigs of memory, or should we treat it as thousands of machines with very fast interconnect, each with a small memory? i.e., can we go to a very large batch sizes if we need to stick to small batch size, but we expect that the communication overload is small?
So for deep learning, you treat that as one big machine. And with respect to the batch sizes, essentially, we support batch sizes from very small batch sizes up to infinity. We use underneath intrinsic gradient accumulation. So we can support extreme batch sizes without any changes in the user code. So our compiler will take care of that. If you program the chip for HPC application, and if you run low-level code, then you will have to take care of instructions which run on every single processing element. But there are tools which will help you to kind of distribute the compute and kind of write not instructions for every one of 100,000 cores, but to tackle them in groups and essentially make the programming a bit easier.
Okay. So then for Natalia, can you elaborate on what other HPC workloads are suitable to run on this platform, and what are the features that make them suitable for it?
I think in our limited experience with HPC, there are two key properties. First, the workload should fit into the memory. That's where you will be the most successful. So if we're talking about something like PD solvers, some stencils codes, or FFT, we want the whole problem to fit into the memory of the chip. And where we are beneficial is especially where those workloads require operations on sparse tensors. So when otherwise you will have kind of GPUs bottlenecked by either memory bandwidths or interconnect bandwidths when you try to distribute the workload across multiple devices, that's where we see many orders of magnitude speed up on our system.
Okay. So do you have an estimate on how much energy your platform could save for large model training compared to current systems?
Yeah, so that depends a lot on the workload. Just in the matter of specs, CS1 draws roughly 20 kilowatts of power, but typically replace a cluster of a small scale cluster of GPUs and train the model faster than a small scale cluster. So depending on the workload, we've seen several times slower. If you measure how power you need to consume to train model end to end, so with the CS1 system, it will be several times lower than with GPUs. But the exact number, again, depends on the workload.
Okay. Does the data have to be explicitly represented as sparse tensors in order to utilize the CS1?
No, we will. So internal representation of the data on CS1 will be in sparse format, but in TensorFlow you can write your code, and most of their implementations are written using just dense representations. You will have your explicit tensors, and on CS1 side, we will replace that with a sparse representation.
What is the CPU core count to WSE ratio required for the Neocortex system? Do you need the full HPE Superdome to feed data and launch work to the WSE?
That's a really good question. And unfortunately, the answer is also depends on the workload. So I think for most of the workloads we've seen so far, you don't need the full Superdome Flex to feed the data. So typically it's enough to run on just a few sockets of the Superdome Flex, and the rest of the system can be used by other users to run either compile jobs or to feed the second CS1 machine. But there are certainly some examples where the model is not compute intensive. So if you have very small multi-layer perceptron and you feed very large tensors into that, you may need the full Superdome Flex to drive that. But we yet to see, I think during our early user program, we haven't seen any workload which requires the full Superdome Flex. So we're yet to see that.
Someone sent a follow-up. Let me find which question they were referring to. So the person who asked, does data have to be explicitly represented as sparse tensors in order to use the CS1? They followed up by sparse tensor representation, I mean something like CSR or CSC.
No, so the answer is, I understood the question, thank you. But in the TensorFlow code and PyTorch code, we don't expect you to represent your tensors in that format. But inside our system, so when the data is passed between processing elements, our internal representation, default representation is compressed raw format, so CSR. But in your code, you don't need to convert the data into that representation.
And then we had another follow-up about the AI cores being optimized. So what does it mean the cores are AI optimized in terms of the architecture of the cores in comparison to a traditional core currently used for traditional simulations in HPC?
Yeah, so we have much higher memory bandwidths. That enables us to, so there are two things. One is much higher memory bandwidths, which allows us to run these vector-vector operations at high utilization. So for a traditional core, a GPU core, a CPU core, you will have memory hierarchy. So you will have very small amount of L1 cache. And in order to keep their compute utilized, you're essentially forced to reuse the data in that cache. And in any implementation of, I don't know, BLAS routine, there are very sophisticated loops to make sure that kind of you reuse the data as much as you can. So with our memory hierarchy, we don't have that requirement, and we can run low arithmetic intensity operations at high utilization. And the second is that the architecture is data flow architecture. So essentially we have a series of operations on sparse tensors. Again, because internal representation of the data is sparse, so we have this compressed sparse row format. So the data which is communicated between different processing elements is just non-zero elements and indices, and it will trigger the next operation only for non-zero elements. So we don't pass zero elements across the network, and we don't do any computation on those, and it's all kind of driven by the data.
All right, thank you. And so Paula, I know that you just answered a question about applications. Do you want to maybe speak a little bit to like the application process for folks who are still with us, just to kind of clarify that?
Sure. As mentioned during my the first section of the webinar, we'll have a very lightweight application process. So it's very low burden. It has been designed to be very low burden because we want to encourage all of you to apply. There were questions regarding whether or not we welcome non-AI HPC applications. At this time, we are encouraging those type of applications. So if you have a non-AI HPC application that you think might be a good fit, please submit a proposal, but we better call it an application. It's not, maybe the word proposal might signal a more involved type of preparation or document. It's not really that involved, it's very lightweight. So I encourage you all to look at the application process, and if you have an application or a workflow that you think would benefit from Neocortex, to apply. We are available to answer any questions through neocortex@psc.edu, and we really look forward to you all submitting your applications, and us. Yeah, we'll make a very thorough digestion of what you submit, and we'll work closely to make sure if your application is a good fit, that we make it successful via Neocortex. I know we are already past the time, so thank you so much, Natalia and Megan, for facilitating the webinar. Thank you everyone for your questions. If there are additional questions, please do use the channels we have mentioned, and please go and apply once the link becomes available. Thank you all.
Thanks, everyone.
Thanks, everyone.